Welcome to the 9th video of our lecture series. So in this video we are going to talk about generalized angular momentum. So we will solve a problem, and while solving this problem we will know basics of this angular momentum, generalized angular momentum. So today we will discuss generalized angular momentum. So here is a problem. So in this problem we have to show, so like this uncertainty in delta j in jx and jy is this, and these are given like this is standard formula of uncertainty of any operator, and we have to show that this relation is consistent with this. So what is this? So this is generalized uncertainty principle. So we have to show that this operator satisfies generalized uncertainty principle. So let us proceed. So suppose we have our generalized angular momentum J. And it has its components, like, so it is in 3D, so it will have three components. So let us use Cartesian coordinates. So it will have three components as jx, jy and jz. So we have z is summation of jx I cap jy. So we know that angular momentum is defined as this. So these operators, so these operators, they represent the observables j, x coordinate of generalized angular momentum, y coordinate of generalized angular momentum, and z coordinate of generalized angular momentum. So, and we define the square of this generalized angular momentum. So it will be jx square plus jy square plus jz square. So this, as this j square is a scalar, so it will commute with all this. So let us check. So first of all, let us introduce the commutation relation between these coordinates of defined coordinates of angular momentum. So we know from standard formula that jx jy is defined as I h cut jz. That means these three, and we have jy jz is I h cut jx, and we have jz jx I h cut jy. So from this we can say that jx, jy and jz, they don't commute with each other, because if they commute, then their commutation relation will be 0, but their commutation relation is non-zero, so that is why they don't commute. But as z square is scalar, so z square commutes with all these three components. So let us verify that. So we have z square. So let us verify for jx first. So we have this as jx square, jy square plus jz square, and we have jx. So first term involves only jx and jx here, so it is 0, and we have the rest two terms. So we have to calculate this and this. So from standard commutator properties, we can write this as jy jx, and we will have another term as jy jx into jy. Similarly, for the second term, we will have a commutation relation like this, and jz jx jz. Now jy jx is equal to the negative of this, so it will be minus I h cut j y j z, and from the second one we will also get minus I h cut j z j y, and from here j z j x is I h cut j y, so it will be I h cut j z j y plus I h cut j y j z. So we can see that this term cancels out, and this will also cancel out, so this is 0. So in the similar manner, if you calculate z square jy, and if you also calculate z square jz, then you can see that this both of them will be 0. So z square commutes with all three. With zx, jy and jz, but these three terms don't commute. So if we want to construct an eigenstate, so then maximally what we can do, so we can construct an eigenstate of which operator? So we can construct an state or eigenstate of j square and any one of the components of angular momentum. So that means we cannot define a state which will be eigenstate of z square and all these three, because these terms, they don't commute with each other. That is why we can construct a state which will be maximally an eigenstate of j square plus any one of these three components. So we can choose any of the components. So let us just choose jz. So you can choose also zx or zy. So that really doesn't matter, that this z axis is not defined till now. So we can take any one of the components. So for convenience we are using this jz. So suppose, so if we want to construct a state which is an eigenstate of z square and jz, then you can find in any standard textbook that this eigenstate is defined as Jm. So what is J and M, and what are the eigenvalues for these operators? So it is given as, so you can find Z square Jm is J into J plus 1 H cut square Jm, and Jz, if it is operated on Jm, it will give us M H cut Jm. So this is eigenstate of both Jz and Z square. And what are the eigenvalues? For Z square we have eigenvalue this, and for Jz we have eigenvalue this. So what are the values of J and M? So basically we have J to be 0, half, 1, 3/2. So these are the value of J. That means J is half integer. And we have M value to be from minus J to J. So that means for each value of J there is 2J plus 1 M values. So for each value of J there are 2J plus 1 values of M. So let us consider an example. Suppose we have J value to be 3/2. So then what will be the value of m? M value will be for j 3 by 2, m is minus 3 by 2, minus half, half and 3 by 2. So there are, we have 4 m values. And if we construct 2j plus 1, so 2j plus 1 will also give us 4. So this is consistent. So now we have to find delta jx and delta jy. That means uncertainty. So delta jx we know is defined as jx squared average value minus jx average value squared and root. Similarly, delta jy will be jy squared average minus jy square average square. So that is these are the terms that we have to evaluate. So what is the formula for delta jx? So it is jm jx jm. Now we can so as in case of harmonic oscillator, where we have raising operator and lowering operator, in case of angular momentum we can also define a raising operator and lowering operator, such that, so this is our raising operator here, and this is lowering operator. So why raising and lowering? So as in case of harmonic oscillator, it makes state from n to n plus 1, raising operator, and lowering operator it brings it down to n minus 1. So similarly, in case of angular momentum, if j plus acts on jm state, it will give us a value h cut root under j minus m into j plus m plus 1, and it will bring the state j plus jm to j m plus 1. That means it will transit the value m to m plus 1, and similarly j minus 1, it will give us a value h cut root under j plus m into j minus m plus 1, and it will bring the state jm to j m minus 1. So that is why we call them raising operator and lowering operator. So this raising operator and lowering operator are defined as jx plus minus ijy. So we can write jx in terms of this raising operator and lowering operator. So jx will be half j plus j minus, and jy will be 1 by 2i j plus minus j minus. So what will be the value of jx if we operate jx on jm? So what we will get? So j plus we can write as this, and we have our jm. So it will give us a value h cut by 2 root under j minus m multiplied with j plus m plus 1, and we have j m plus 1, and there the second term will give us root under j plus m multiplied with j minus m plus 1, and we have the state j m minus 1. So that is the function of jx on jm. So if we operate jx on this eigenstate of j square and jz, we will get a superposition of this state and this state. So what will be jm jx jm? That means expectation value of jx. So it will be like jm with some, so here we will have a coefficient term into state Jm plus 1 and another coefficient into Jm minus 1. So this term, this Jm terms, these are orthonormal as in case of harmonic oscillator. So these are orthonormal. These basis states are orthonormal. So that is why Jm plus 1 and Jm minus 1 both will give us 0. So that is why we have Jx to be 0. Similarly, if you calculate Jy, so Jy we can write as 1 by 2i z plus minus j minus, and if we operate Jy on Jm and take the expectation value of Jy, that means Jm, Jy, Jm, then similarly due to orthonormality of these Jm's we will get this to be 0. So now we have to calculate two more terms, Jx squared and Jy squared. So let us proceed. So what will be the Jx? We can see that Jx is half J plus J minus. So Jx squared operator will be 1/4 J plus J minus multiplied with J plus J minus. So that is our operator. So we have here J plus squared plus J minus and J minus J plus we have J minus squared. So if we want to take the expectation value of Jx squared, so what will be the value? It will be 1/4 J plus squared expectation value plus J minus expectation value plus J minus J plus expectation value plus J minus squared expectation value. Now we can clearly see, so if J plus act on a state Jm, it will give us a coefficient, suppose C, into Jm plus 1. So if we operate again J plus, so what will be the state? It will be another coefficient. So let us denote this by A, and we will have Jm plus 2. So Jm, J plus squared, Jm, this will be 0. In the similar manner, J minus squared Jm, it will give us another coefficient and the state will be m minus 2. So here also expectation value of J minus squared will be 0. So this is J minus squared expectation value and this is J plus squared expectation value. So this term and this term, they both are 0. So what will be the expectation value of J square on state Jm? So for state Jm, the expectation value of Jx squared would be 1/4 J plus J minus plus J minus J plus. In the similar manner, we can write Jy. We know Jy is 1 by 2i J plus minus J minus. So what will be Jy squared? It will be minus 1/4 J plus minus J minus, and we will have another J plus minus J minus. So it will give us minus 1/4 J plus squared minus J plus J minus J minus J plus J minus squared. So similarly, expectation value of Jy squared will be minus 1/4. So first time expectation value we have already calculated to be 0 here, and last time expectation value that we have also calculated to be 0. So it will be minus J plus J minus minus j plus. So we can see that this is exactly equal to jx squared. So expectation value of jx squared and jy squared are same. Now we know that j squared is jx squared plus jy squared plus jz squared. So expectation value will be this. Now since jx squared expectation value or jy squared expectation value are same, so we can write jx squared expectation value equal to jy squared expectation value to be half of j squared expectation value minus jz squared expectation value. So since this jm is eigenstate of both j squared and jz, so we can easily calculate these two values. So what will be jz squared? So it will give us j plus 1 h cut square into jm. So if we calculate the expectation value, it will be j into j plus 1 h cut square. And similarly, if we calculate the expectation value of jz square, it will be m square h cut square. So these are our expectation value of j square and jj square for the state jm. So let us put this. So what we have to calculate? We have to calculate jx squared expectation value. So this comes out to be half. Let us take h cut squared common, and we have j into j plus 1 minus m square. Similarly, we have jy squared expectation value to be h cut square by 2 j into j plus 1 minus m square. So what will be the uncertainty in jx? So it is root under jx squared minus minus jx squared. So this term is 0, so it will be root under jx. So that means h cut by root 2 into root under j into j plus 1 minus m square. And what will be the delta jy? It will have same value. So h cut by root 2 into root under j into j plus 1 minus m square. So we have to find out the product. That means we have to find out delta jx into delta jy. So what will be its value? So it will have the value delta jx, delta jy. So since both are same, so you can write this as delta jx squared. So it will be h cut squared by 2 into j into j plus 1 minus m squared. So now we have to solve the second question. So what it is stating, we have to show that this relation that we have just recently get this, it is consistent with our generalized uncertainty principle. So let us proceed. So we have our relation. So what we know about j and m? We know that j must be greater than equal to m, because we know for a value of j, what are the m values of m? So it is minus j, from minus j to plus j. So j minus 1 j. So that is why j must be greater than equal to m. So this term j into j plus 1 minus m squared, this must be greater than equal to m into m plus 1 minus m squared, as j must be greater than equal to m. So we get it is greater than equal to m. So delta jy, delta jx, it must be greater than equal to m h cut by square by 2. So we can write this one as h cut by 2 product with m h cut. And what is m h cut? M h cut we can write as jz expectation value, and we can take its mod. So we can write from this relation and this one, we can write delta jx, delta jy, it must be greater than equal to h cut by 2 into the modulus of the expectation value of jz. So this is our desired result. So this is generalized uncertainty principle. So that is it for this problem. So let us now move with our second problem. Okay, so let us now solve this question. So this question appeared in JEST, I think. So what it is stating, so it is related to this angular momentum, so what we have discussed just now. So here we have a particle that is prepared in a simultaneous eigenstate of L square and Lz. So we have discussed about generalized angular momentum. So if we have only orbital angular momentum, then we can replace J by L. So J is for generalized case. So it can be orbital angular momentum only, or it can be spin angular momentum only, or it can be a combination of both. So basically this is angular momentum. So if we have orbital angular momentum, then we will use L. So all the mathematics are same. So basically particle is prepared in a simultaneous eigenstate of L square and Lz. So what we have already discussed, like J square and Jz eigenstate. So if L into L plus 1 h cut square and m h cut are respectively the eigenvalues of L square and Lz, then the expectation value of L square, what we have already calculated. So we have to show that this expectation value satisfy which relation, like is it 0 or is it in the which range, we have to find out. So first of all, we have already found out that the expectation value of jz square is h cut square by 2 into j plus 1 minus m square. So in case of orbital angular momentum, Lx squared would be h cut square by 2 L into L plus 1 minus m squared. So that expectation value is for like Lm eigenstates. So if Lm is the eigenstate of our system, then Lx square expectation value will be this. So we have to find out the range within which this Lx square expectation value lies. So we know that what is the value of m for a fixed value of L, we have m values to be minus L, L plus 1, and we have L minus 1 and L. So what is the maximum value of m? Maximum modulus value, so it can be L, and minimum modulus value is 0. Since we have here m squared, that is we are interested in modulus value, because anyway m for m value L and for m value minus L, both will give us same m squared value. So that is why we are interested in only the modulus factor. So it minimum can be 0 and maximum can be L. So if m is m max, then we will have Lx square to be h cut square by 2 product with L plus 1 minus, so what is the maximum value? It is L, so we have L square, so that means h cut square by 2L. And so when m is maximum, when we have m maximum, we have expectation value of L square to be minimum. That you can easily understand, because so here is a minus sign, so the greater the value this, the lower the value will be this. And when m is m minimum, then we will have Lx squared to be maximum. And what is this maximum value? So this is our minimum value. And what is our maximum value? So maximum value is h cut square by 2 L into L plus 1, because for maximum for L maximum we have m value to be 0. So what is our correct answer? So Lx square lies in the range from so what is the minimum value? Minimum value is h cut square by 2L. Sorry, so it can be, it must be greater than this. So Lx squared value, it must be greater than this, and it must be less than h cut square by 2 L into L plus 1. So less than equal to and greater than equal to. So let us check which is our correct option. So yeah, so option D is correct. I mean Lx square value, it must be greater than this and it must be less than this. So this is our correct answer. So let us move to the last problem of today's video. So here we have the case where we have j value to be 1 and we have to find the matrix representations of these operators. So let us solve this. So we have here j value to be 1. So what can be the possible m values? M values are -1, 0 and 1. So what are the possible states? The states are 1, 1, 1, 0 and 1 minus 1. So these are eigenstates. Eigenstates of what? Eigenstates of j squared and jz. So we have to find, so these are our bases. So as we have to find this matrix matrix, so suppose we want to find the matrix representation of operator j squared, then we have to find all the matrix elements. So matrix we will represent, so in this so this is 1, 1, this is 1, 0 and this is 1 minus 1, and along this we have 1, 1, 1, 0, 1 minus 1, and we have here this element will be 1, 1, jz square 1, 1. So this we should write as get this all. So this element will be 1, 1, jz square 1, 0. This element will be 1, 1, jz square 1 minus 1. Similarly, we can write all rest of all 1, 0, jz square 1, 1, 1, 0, jz square. We have here 1, 0 and 1, 0, jz square 1 minus 1, and for the last one we will have 1 minus 1 jz square 1, 1. Here we have 1 minus 1 jz square 1, 0, and here we have 1 minus 1 jz square 1 minus 1. Now since jz square, these are eigenstate of jz square, so we know that j m jz square j m dash, it will be 0 for m not equal to m dash if they are different, and it will have the value j into j plus 1 h cut square for m equal to m dash. So using this relation we can write the matrix element, the matrix representation of jz square operator. So this term we will have j value is 1, so we have 2 h cut square here, this is 0, third term is 0, similarly this will be 0, this will also be 0. So let us first write down which will be zeros. So this is 0, this is also 0, and this term, so j value is same for all, so this or both the terms will be 2 h cut square, because j value is 1 for all the eigenstates. We have m values to be different, but j is 1, so that is why z square will produce 2 h cut square for all this. So this is our matrix representation of z square. Similarly, now we have to find matrix representation of jz. So we can write also jz like this. So here we have, so similarly the same is the case for jz also. So for jz, if m and m dash are different, so it will be 0 for m not equal to m dash, but if m equal to m dash, we will have m h cut. So this state, here we have m value to be 1, so that is why it will give us h cut, this 2 will be 0, and here also these terms are also 0, and this has m value to be 0, so this will give us also 0, and this has m value minus 1, so this is minus h cut. So if you look carefully, then you can see that this z square and jz, they are already, these two are diagonalized. Why they are diagonalized? Because we have these states which are eigenstates of both z square and jz. So as they are eigenstates, so that is why if we represent the z square and jz in matrix form in this basis, so they must be diagonalized. So now we have to calculate j plus minus and j x and jy. So let us proceed with the case of j plus. So for j plus, what is j plus jm? So it will give us root under j into j plus 1 minus m into m plus 1 into j m plus 1. So that is j plus. And we have j minus to be root under j into j plus 1. So we have here h cut multiplied minus m into m minus 1 j m minus 1. So this j m dashed and j plus j m. So what will be the case? It will be 0. When it will be 0? If m equal to m dashed. So if both are same, then we will have 0, because this term will give us m plus 1, and m dashed, or if m dashed is m, then we have the state jm plus 1. So that must be 0. And if we have for different values, we have to calculate. So let us calculate this for 1 1, and here we have suppose 1 0. So this term will give us h cut, j value is 1 and m value is 1. So if they are same, this term will produce 0. So that is why this expression will be 0, because because this value for this state we are getting 0. So j plus 1 1 it will be h cut 2 minus 2 1, and so since m value cannot be 2, so you can easily see that this should be 0, and also we are getting this as 0. And what will be j plus for 1 minus 1? So it will give us h cut root under 2 minus m value is minus 1, so we are writing this as plus 1, and we have here 1 minus 1. So and it will it will bring it back to 1 0. So root 2 h cut 1 0. So z plus on this is giving us this, and z plus 1 1 1 giving us this, and also calculate what will be z plus 1 1 0. So for 1 0 we are getting also root 2 h bar, and it will produce 1 0 to 1 1. So let us calculate all the terms. So 1 0, and what will be z plus 1 minus 1? So 1 minus 1 will give us root 2 h bar. So that is one matrix element, that is another matrix element, and we have this matrix element to be 0, because this m and m dash, they are same. So similarly we can calculate for different states. So 1 minus 1 j plus, so 1 minus 1 j plus, and here we have 1 1, so j, this expression will give us 0, so that is why this element is 0. Now we have 1 minus 1 j plus 1 0, so j plus 1 0, this will give us root 2 h bar, and 1 minus 1 1 1, so this will give me 0, and we have one term which is z plus 1 minus 1, so this will also be 0, because m and m dash are same. And similarly where we have the last expression of 1 1, so here we have 1 1 must be 0, 1 1 j plus 1 0, so it will give us root 2 h, and 1 1 j plus 1 minus 1, so 1 minus 1, it will bring it back to stage 1 0, so which is orthonormal to this, so this will also be 0. So if I want to write the matrix form of j plus, so what will be our form? So 1 1, first of all this term we are getting 0, then this term we are getting as root 2 h bar, and this term we are getting as 0, then we have 1 0, and this is 0. So let us just write down the elements. So we are also getting this as 0, and this is we are getting as root 2 h, and let us the last 1 minus 1, this is 0, 1 minus 1 1 0, this is also 0, and 1 minus 1 1 minus 1, this is also 0. So this is our expression for z plus. Now similarly you have to calculate j minus. So let us first do this. What will be the value of this? So it will give us h cut to j into j plus 1 minus m into m minus 1, and we will have 1 0. So it will give me root 2 h bar 1 0, and j minus, if it acts on state 1 0, what will be the value? So if we put m value to be 0, so it will be root 2 h bar 1 minus 1, and if we apply j minus on 1 minus 1, so this is the lowest value of m, so if we apply the operator, it will not be able to, so there are no states below this, so that is why this will give us 0. So let us calculate these matrix elements now. So first 1 1 1 1, so as m values are same, it will give us 0, and for the second term we will have 1 0. So just calculate these terms. So root 2 h bar, we have here 1 1, and here we have 1 minus 1. So this will also be 0. And what will be the third term on top of the first row? So this will be 0. So all the terms of the first row is 0. Now we have 1 0, j minus 1 1. So j minus 1 1 will give us root 2 h cut 1 0, and we have here also 1 0. So it is root 2 h cut, fine. Then we have second term of the second row 1 0. Since these two are same, we will have this as 0. And for the last term of the second row, we will have 1 minus 1. So this term will give us 0. So that is why it is 0. And let us calculate the third row. So for third row, so we have j minus, so what is its value? Root 2 h cut. We have here 1 minus 1, and it will be 1 0. So orthonormal, so it will be 0. Now we have 1 minus 1, the second term of the third row. So 1 0, and z minus 1 0, we will bring it to root 2 h cut. We have 1 minus 1 here, and we have 1 minus 1 here. So it will be root 2 h cut, and the last term of the third row, it will be 0, because m values are same. So what is our j minus matrix matrix? So j minus matrix we can write as all the elements of the first row are 0, and in the second row we have our first element to be root 2 h cut, in the second one and third one to be 0, and in the third row we have first one to be 0, and the second term we have as root 2 h bar, and we have here 0. So this is the matrix representation of j minus. So what will be the matrix representation of jx? So jx we know is half j plus j minus. So it will be, so root 2 h cut we can take common from both j plus and j minus, and we have j plus to be, so let us just close this. So it is 0 1 0 0 0 1, and we have all terms here 0, and j minus we can write as 0 0 0 1 0 0, and here we have 0 1 0. So what is jx? Jx h cut by root 2, and we have here 0 So that is our matrix representation of jx. And what will be the matrix representation of jy? So jy we know is defined as 1 by 2i j plus minus j minus. So if we do the similar type of calculation, we will get h cut by root 2i, and here we will have like j 0 1 0 minus 1 0 minus 1 0 1 minus 1. So if we write down, so you can write this as I h cut by root 2 0 minus 1 0 1 0 1 and 0 minus 1 0. So this is our matrix representation of jy. So in this way you can calculate matrix representation of any operator. So what is the process? So first you have to identify the basis. So to represent any matrix, so every matrix have its eigenvalue and eigenbasis. So first you have to know in what basis you are expanding the matrix. So first if you identify the basis first, then you have to just calculate the matrix elements. So what are the matrix elements? So matrix elements is just we have to sandwich the operator between this different basis. So in that way you can calculate matrix representation of any operator. Okay, so that is it for today's video. So we will meet on the next one. Okay, so in JY I have a little calculation mistake. So we will have here plus 1 and we will have here minus 1. So if I multiply this I with in here, so it will be I, and we will have this term to be plus I, and we will have this term also to be plus I, and we will have this term as minus I. Okay, so this is fine now.